Hi, welcome to a series of webinars on Optical Transport Networks. This is your friend Brahmanan GS. Let's discuss today why we went for OTN, Optical Transport Network, Optical Transport Hierarchy. Initially, we were using SDH transport networks. It had standardized mapping for client signals. It had enhanced PM at multiple layers, very comprehensive fault detection and isolation techniques. But SDH was based on time division multiplexing, and also it was mainly based for voice, not data, though it has supported lots of client signals for IP, ATM, FC, etc. But it was based on voice. We know we are all greedy people for data now, and the ratio of voice to data is moving towards data. And SDH provided granularity starting from 2 Mbps till STM1 level, 140 Mbps level. As we are moving towards very high data rate, I want my switching rate coming closer to my lane rate. What's the point in switching at lower rate when there is no need for it? Who is asking for 2 Mbps? Who is asking for 34 Mbps? I have 100 Mbps IP based internet connection to my home. So why does one need lower granularity? So because of all these reasons, people started using WDM networks. We know SDH was based on 1 lambda, but optical fiber can support multiple lambdas without interference between each lambda. In each lambda, I can transfer and transport very high data rate, starting from 10 Mbps till 10 Gbps to 100 Gbps through my lambdas using WDM networks. But did WDM at the initial stages, did it support the standardized mapping of client signals? No, it didn't. So if a customer is providing 1 GB of data, and if my wavelength which was supported in my WDM network is for 10 Gbps, then I am supposed to do a demultiplexing at every carrier boundaries from 10 Gbps to 1 Gbps, take out my 1 Gbps and do again multiplexing and so on. So there was a lack of standardized mapping and lack of standardized fault detection and isolation. Fault cannot be communicated efficiently from one operator's domain to other operator's domain. So if somebody receives a very bad signal, there was no mechanism to communicate and find out the root causes efficiently in WDM networks. Lacks of FCAPS functionalities in WDM. No, it was a huge liability for interconnected networks in providing the quality of service. We know that DWDM can provide and it can handle traffic at wavelength layer starting from 10 Gbps till 100 Gbps, and which based on what interfaces we use. But we need to question ourselves, did WDM provide any way to fill in the partially filled wavelengths? If an if there is a DWDM network element and I need to transfer the data, if this particular you know um, equipment supports n number of lambdas, all these lambdas travel in this optical fiber. If one lambda is supporting 100 Gbps, if my customer provides only 10 Gbps from location or from NEA to NEC, then this lambda carries only 10 Gbps. So it uses only 10% of the complete bandwidth. So this was the biggest, disadvantage with DWDM. So it was not able to fill the wavelengths completely. We can look at one of the videos in our last slide in this session to get the difference between optical switching and digital switching. The next question we should ask is, can DWDM provide clock info, a start-stop indication of the packet, error checking, error connection to take IP traffic directly? Can DWDM network take IP traffic directly? Can support these kind of mechanisms? The answer is no. Now, how about path level monitoring in WDM? If suppose there is a customer, there is a carrier A, and who has to transfer the data from location A to location B, if it happens to traverse in somebody else's network, how can he manage his paths, which was not supported here? Now, we need to understand why we really went for optical transport network. I need more granularity. I don't want my switching to be at lower rates. And operators want to provide end-to-end service. There should be a proper handshaking mechanism from one operator domain to another operator domain. It means that there should be a proper operation, administration and maintenance provisions for good manageability, which was lacking in WDM networks, which is very much supported in OTN through its overhead bytes. Transparency of client signals, support for both legacy and emerging formats. It should keep supporting SDH, SONET, IP, ATM, FC, etc. All the client signals transparently, which is well supported by OTN. Support for sub-lambda switching to enhance efficiency. Easy upgrade and bandwidth on demand. I should be able to add bandwidth wherever it is of demand. So this is clearly linked to sub-lambda switching, which we will going to see it in our last slide. Cost for bit transported should be cheaper than SDH SONET. Let's look at the standards which define OTN. The network architecture is defined in I280 G872, structures and mappings in G709, G709 is one of the key standards for OTN. Equipment functional specification in G798 and equipment management function in G874 and jitter and vandal performance in G8251 and OTN protection in G OTN Part 1-2. G709 provides us optical transport hierarchy. OTN is also called as is a digital wrapper because it takes all the client signals, it wraps onto optical channel. G709 was initially standardized for 10 Gbps line, 10 gigabit Ethernet, and later to support the lower order client signals, it started supporting ODU 0, ODU 1, ODU 2 as well. So ODU 0 can be mapped onto Optical Transport Unit 1 and 10 Gbps can be mapped onto ODU 2 and so 40 Gbps can be mapped onto ODU 3 and similarly 100 Gbps can be mapped onto ODU 4. See, there is an hierarchical structure as standard which is well defined in G709. This is a simplified version of hierarchy. For detailed version you can refer to G709. And today there are equipment manufacturers who are able to provide the OTN network elements supporting up to 500 Gbps and targeting for 1 terabits per second. The biggest benefits of adopting OTN by operators for the fundamental reason is better bandwidth management. See, in the SDH, the grooming was at the rate of 2 Mbps. Whereas take for example WDM, using ROD, reconfigurable optical add-drop multiplexers in WDM, the grooming was at 10 Gbps, 40 Gbps, 100 Gbps. We wanted the better bandwidth management through some data rate ranging in between these. So OTN started supporting ODU 0 for 1 Gbps, ODU 2 for 2.5 Gbps. So which helps better bandwidth management. Next biggest advantage is switching scalability. Assume I have a SDH 64 or STM 256 or STS 768. If I want to put in 410G to 40G SDS Sonnet Max, I'll have to do the switching with the rate of VC4 and STS1. Imagine I'll have to do the switching with 256 VC4 and even worse in Sonnet with 768 STS1. So which abundantly increase the management and operational cost and efforts in it. So using OTN, the switching rate kept on increasing with the advance in line rate. So starting from 2.5 Gbps till 100 Gbps, the switching rate is possible in OTN. And the next benefit of OTN is long reach and better bit error ratio. Now, better bit error performance means better signal strengths. I mean, which helps me in taking my signal for a long duration in time. So how is this better bit error ratio performance is provided in OTN? It is provided by supporting forward error correction. So we'll discuss forward error correction in a separate session, but just for time being, let's understand that there is a provision in OTN overhead bytes wherein forward error correction is supported, which enhances, which provides the coding gain of up to 6.2 dB. It means that I can extend my span, which is equivalent, whose loss is equivalent to 6.2 dB. And one more biggest advantage of OTN compared to traditional SDH SONET is the hierarchical support for tandem connection monitoring. We know in SDH there was only one tandem connection monitoring provision, whereas in OTN there are 6 levels of tandem connection monitoring. I can provide tandem connection monitoring between any operator to any operator for quality of service, for end-to-end path supervision, for even protecting a particular path within an operator's domain. That is possible in OTN, which was not possible in SDH and SONET. Efficient switching of packet traffic. See, we should not consider OTN as a typical traditional transport protocol. This is an aggregation protocol. This is an switching protocol as well in the context of its ability. See, most of the data is transit based. I mean, it comes in and it goes. I mean, there is very less data which might be dropped or added in the current environment when the huge data traverses from one location to foreign location. So most of the traffic could be transit based. So what is the point in taking or considering the IP MPLS architecture in such scenarios? So if you use this IP MPLS architecture with WDM, every time the switching goes to layer 3 gets switched on, and it groomed back to the layer 1, and then the data moves ahead. But the beauty of OTN is it uploads the switching which was supported by IP MPLS to optical layer, that is layer 1 itself. So, and this particular offloading capacity of OTN switches helps very much between very fixed locations. This leads to improved latency. This helps banking and financial sector, because if the routing takes place within the optical layer, the switching time is quite very less. So its improved latency helps these sectors abundantly. And reduced capex and opex. See, cost per Gbps of switching capacities is cheaper for OTN compared to routers, and because the quantum of equipments used in SDH and to some extent in WDM is costlier compared to OTN, and better reliability over IP MPLS because of the kind of uh, protection mechanisms supported in OTN, so which improves the operation expenses, reduced power consumption. See, OTN uses less fabric compared to SDH, as grooming is in 1 Gbps and above, whereas SDH grooming is between 2 Mbps to STM1. So it means that less equipment means less power. Less power, it means that less operational expenses. Just want to give an example that the power tariff, for example, in Bangalore, India, has increased by many folds. So, can't this be one of the biggest reasons why we should consider the OTN? Better DWDM utilization. See, we moved from SDS to DWDM because DWDM provided multiple lambdas. So each lambda carried huge data. That was wonderful. That's good. But did we efficiently use DWDM? So the switching mechanism in WDM is optical switching, whereas in OTN it is digital switching. So OTN supports audio cross connects, which we'll discuss in a separate session, which supports sub-lambda grooming through digital switching. So the main catch of this sub-lambda grooming is it keeps each link separately from each other. So I can take out any link or any data at any time. So this OTN supports OTN channel with optical overhead. So comprehensive OEM provisions are supported through OTN frame. So overhead will be discussed in separate session. I just want to show you a video which nicely describes the fundamental difference between optical switching and digital switching. I just want uh, you folks to watch this video, which will be coming up, which is a video from one of the manufacturers, Infinera, so which is one of the leading manufacturers for OTN network elements.
Welcome to a short video on transport network architectures. In the next few minutes, we look at two key architecture choices, wavelength switched and digitally switched network services. The two key architecture choices for transport networks are optical switching and digital switching. Optical switches, or ROADMs, operate at the wavelength level, and services carried by those wavelengths are trapped in the wavelength until they're converted back into digital signals. In very general terms, optical switching works well when the service data rate is the same as the wavelength or line-side data rate. In contrast, a digital switch can reach inside the line-side wavelength and process sub-wavelength services using an OTN switching and multiplexing framework. Such wavelength services can be redirected or groomed together to fill the line side more efficiently. Digital switching works well when the service and line side data rates are different, especially when the service data rate is less than the line side data rate. let's look at the impact of these different switching architectures on overall network efficiency using a simple 8-node network configuration. For simplicity, we consider only 10G service demands from node A. All the service demands will be transported over 100G wavelengths on the line side. There are 3 10G services traveling over the blue wavelength from A to D, 2 10G services traveling over the green wavelength from A to H, and 2 10G services traveling over the red wavelength from A to F. So let's check the efficiency of a network that uses only optical switching. Between nodes A and B, we see that we need 3 wavelengths, each with 20 or 30% fill. And we have 2 wavelengths between nodes B and F, each with 20% fill. Now, staying with an all-optical switching architecture, let's add 1 10G service from node A to node G. This adds yet another wavelength, shown in brown, with only 10% fill. While this may seem like a low-demand architecture, it's exactly the way that services are added to real networks in the early days of that network deployment. Let's keep the same scenario as before, but change the architecture of the transport network. Specifically, let's introduce digital switching at each node. Services can now be digitally groomed, not only at the entry points in the network, but at intermediate locations such as node B, to keep an acceptable fill rate for all wavelengths as traffic patterns evolve. All of the services originating at node A can now be carried on just one wavelength, and this wavelength has a fill rate of 80% in our example. The switching capability at node B allows the services on the incoming wavelength from node A to be divided up and sent towards nodes D and nodes F and G without requiring additional dedicated wavelengths. The availability of switching anywhere in the network allows the total wavelength count to be minimized. Fewer wavelengths mean fewer modules and system chassis, thus lowering overall lifetime costs, including power, space, and operations. To find out more about the value of integrated OTN switching, check out our white papers and the other information at infinera.com.
So this video clearly demonstrated what was the difference between optical switching and digital switching and the efficiency of digital switching. In summary, OTN is like a midway batsman in cricket. The importance of midway batsman in cricket is quite very high. It optimizes packet switching layer above and DWM layer below by providing lower OPEX and CAPEX, enables multiple service providers to synergize to leverage each other's network to improve coverage and provide seamless end-to-end services. So I think this is the reason why we should embrace and adopt OTN networks. Thanks for watching. This is your friend Brahmanan GS. Please subscribe to my channel if you find this is interesting, and if you like my webinar, please click on like, and if you have any comments to make, please do write your comments. Thanks for watching.